to explain the basic property of class patterns. Class pattern is an underlying structure to define a cluster algebra, but in many cases, class pattern itself is the main object which you want to study. So I first 10 minutes say I recall the important part of last lecture. So in order to define cluster patterns, first you have to fix some natural numbers or positive integers. It is called rank, and also fix semi-field, which is considered as the domain for so-called Y variables. Yes, and then from this you consider a field, an ordinary field, which is a rational function field, with is a coefficients field constructed from this semi-field QP with some formal variable W1 to Wn. You really don't have to care what is the role of this one. This is just a formal variable, and this field is called ambient field in the context of cluster algebra. It's just a name. Okay, and now cluster pattern is defined as an assignment of a seed for on a regular N tree. It is a tree graph, and particularly edges are labeled by 1 to n, and the cluster pattern is assignment of a seed for each vertex of this regular N tree, yeah, where this seed itself consists of a triplet. First one is skew-symmetrizable matrix of size n, and then also a tuple of x variable which sit in this ambient field, and also a tuple of y variable which sit in this semi-field. Okay. So those are seed, and the cluster pattern means when two seed are in the next to each other in this configuration of T and T prime, which is connected by edge with labeled K, then it satisfies a mutation. So mu prime is obtained by mutation of sigma T and vice versa. Yeah. And there is some complicated definition of mutation. And first question when you first study cluster algebra is why this mutation is good at all. And the answer will be given gradually. First, it satisfies a nice so-called Roland phenomenon, and that is actually a motivation for the definition, but it also satisfies a nice finite type classification, which was just explained by Jacob, and also and the second and in that important fact is it satisfies the separation formula. This is a justification, and maybe that is enough. Yeah, but there is also more intrinsic meaning of this mutation. But I don't have time to explain everything. But anyway, I'm going to explain a separation formula, and for that purpose, you now need to fix some particular point of your tree graph. It's an arbitrary choice. You can name it, and it is called initial point of the graph. So you have some tree graph, and you fix some initial point. And the purpose of studying a cluster pattern is to express those things using this initial variable sitting at initial point. Yes, and for that purpose, for given such a cluster pattern, you assign three things, which is called C-matrices, G-matrices, and F polynomials. And at each these are defined by our initial condition at initial point, and also our mutation formula, which uniquely determines those things. And that mutation only use family of this exchange matrix, coming from this seed, cluster pattern. Yeah. So anyway, those data are uniquely determine what is called C matrix at T, and T is any given point, and also G matrix. It's integer matrices, and also polynomials, f of it, y, it is called f polynomials. And there are n, 1 from 1 to n. Yeah. So this is a situation. And those are also defined by similar mutation formula. And at first sight, the meaning is not clear. But nevertheless, the main point is it is satisfies the following separation formula, which is very, very important. Yeah. Which is next important to the Laurent property. And it means x variable at a given point is described by this one. So by initial x and y are initial variables. So I don't write xt0 but for simplicity, and just write xj. And so this we have a monomial given by this G matrix at T, like this. And we have some less term, which is, of course, not a simple one, but it is described by the following manner. And here y hat, y is an initial y hat variable, which is determined by the following formula, bji. Sorry, it's okay. And with a t, it means it is initial, initial. Okay, so this means this is initial. Okay, so this is some formula. And y of yt is now represented by your initial y variable using this C matrix, like this, and also product of F matrix at T evaluated at P multiplied by Bji of T. Okay. So this is a main result of this Cluster Algebra 4 paper by Fomin and Zelevinsky. And I'm going to explain how good this formula is. Yeah, you know, those x and y is very complicated. Mutation is determined by the mutation formula, and also those are determined by some mutation formula, which is not a simple one. So only with this formula, it just make a difficult problem to another difficult problem. Yeah. But what I'm going to explain is actually its formula tells you many important things. First of all, those two things are quite closely connected. And it shows some duality structure between those variables. And also, we have some separation of these things, and this separation is a very good one. And I'm briefly explain first, and this is my subject. So somehow, I first of all, this part is regarded as a tropical part. I'm going to explain later more precisely, but at the beginning, very simple way. And this part is considered as a non-tropical part. You know, this is just a simple Laurent monomial, and this is some other things. And this separation is actually a good one, and so it's considered as a leading term of this variable. And then what I'm going to explain is there is actually has the same structure for x variable 2. And first of all, I want to claim that this first leading term, maybe this one, is connected by very simple duality. Yeah? And those variables are related to each other. Yeah? And moreover, what I'm going to explain, and the goal of today's talk is as a slogan, I tell you first that this tropical part, which only has information of very complicated, it just gives a contains a leading term or information of the more complicated object, but this part uniquely determines non-tropical part. That is most important things which this separation formula will tell us. It means complicated mutation formula can be reduced to very much a simpler mutation formula for these tropical variables. That is a statement, and that I'm going to explain you in this my second lecture. So first of all, I explain why this is considered as a tropical part. So I will give a notion of tropical y variables. To explain this, first consider the following setting. So we consider a class pattern for any kind of semi-field, but we particularly consider most general one. General one is called universal semi-field for a formal variable. Those are formal variable. I recall you that it is a semi-field of rational functions with positive rational expression. Yeah? And so temporarily those are different things, but we soon identify these two things. So that's why I use the same symbol. Now we consider also what is called Y pattern. With this coefficient. So Y pattern, I use this notation here, say Y of t. It is an assignment of Y seed for each vertex. Yeah. And we consider the coefficient with coefficient in these are semi-field, yeah? So Q plus Y. So everything is a rational function of your initial, this Y variable with a positive expression. And so it means this YT is actually a pair of skew-symmetrizable matrix and and a tuple of elements in this one, which connected by the mutation formula. But we particularly consider the following initial condition, such that it satisfies the following initial condition, such that it satisfies this initial variable is exactly taken as this formal variable. In other words, you start from algebraically independent variable and you stick to calculate using this variable. Yeah. So this choice is somewhat important in my talk. So you start from y variable and you express everything using this y variable. That's it, assuming this algebraic independence. Now it's time to recall your more explicit formula. What is a mutation? Yeah. So mutation, when you have such arrangement, then y variable at t prime I is related by the following formula: t inverse when I is k. Is the simplest case, and otherwise it's a little bit more. So it's a multiplication of original one times some formula. Yes. Just let me write it first. Yeah. T. Everything is T. Okay, so this is a formula. And this bracket, I recall you that it is when A is positive, it is A. And if A is negative one, it is 0. Yeah. Okay, by the way, in this setting, this plus is just ordinary plus here in a rational function field. So you just consider as the ordinary operation. Ordinary plus in Q plus QY, yeah? It's a subset of this one. Okay, now we apply the tropicalization map. Well, I recall you what is a tropicalization homomorphism. It is a map from this universal or semifield to a tropical semifield, which consists of Laurent monomials like this, and AI are integers. Yeah, and here we have a special sum plus. It is called a tropical sum, where the definition I gave yesterday, tropical sum. And such a way that why the generator, the variable just sent to this one uniquely determine the tropical semifield homomorphism. Yeah, this is the definition. Now, what is the result? Applying this to this one, the answer is simply it is given by this. That's why I call this tropical mode. So. That the image of this tropicalization of your y variable at point t is, of course, is something like this, yeah. But this something here, so it is a Laurent monomial of such things, and the exponent is exactly given by this C matrix. Yeah? So this is C matrix. In fact, for their paper, this is a definition of a C matrix, and they derive the mutation formula, but I somehow do it in the opposite way. And since this is so that's why we call this tropical y variable, yeah, naturally. So in a slogan, C matrix is tropical y variable itself. It contains data. And proof is actually explanation. It's very simple. So maybe I write this here. Maybe I here. You just, first of all, let's temporarily assume that this is not a C matrix already defined, but it's just a coefficient given by this tropicalization. Yeah? And let's see what formula should be satisfied. And initial one, initial condition, because we start from this particular condition, so it gives you exactly this C matrix, yeah, is identity, which is a good one, and also now you specialize this. You just plug in this expression to this one, and let me simply write it. Yeah. And it looks as follows, yeah. So maybe I change some notation, but it's not important. Ti, no. C, product is always 1 to n, so I omit this one. So T prime, yeah. Left hand side of this is, and you just write everything explicitly. I'm going to give a proof of this one, right? So YL, L, K, T, when I is K. And as a part, which I write, Y, L, C, L, I for the first factor. And for the second factor, we have L, Y, L, C, L, K, T, B, T, K, I plus. And finally, we have here tropical sum here, because we consider the image inside this tropical things, and so this is a tropical sum, and Y L C L K T minus B K I T. Okay, some formula, yes. And let's digest this, just because this formula exists, so should be satisfied under the evaluation, so under the specialization. So you compare, we have the following formula, C prime, Li. So just compare the power of a variable y0, gives you from first one minus C L K T I when I is K. And from the second factor, we have CLI plus sorry, CLT plus CLK T from here, and with multiplication of this factor BKIT plus, and now we want to calculate this one, right? So this is a kind of a main point. We first write this portion first, and what is this one? So sorry, I wanted to write this portion later, but only this minus sign I write here. And so this is just taking the minimum, yeah, minimum. This is by definition of tropicalization sum. This is YL of zeroth power. So you compare this with this one, yeah, C L K T, yes, and this power, and minus is already assumed. And then you recognize that this portion can be conveniently written using this symbol that minus CLK plus. You can check it if it is positive numbers, and they coincide. In two cases, it is positive or negative. Okay. So, by the way, this formula is exactly equal to the mutation of C matrix, which I wrote yesterday. You don't have to remember it, but you just wrote yesterday, yeah. And did exactly this formula. So this statement was given. So in fact, so this is the origin of this mutation formula. Okay. Now, so first I identify this part, namely this C matrix part, as a tropicalization of your universal Y variable. Now I'm going to kind of analyze the whole structure of that separation formula, and in the next stage we need a very important cell called a sign-coherence cell of C matrices. And so this one property, which I'm going to explain, was conjectured by Fomin and Zelevinsky paper, and subsequently proved by the following one. Firstly, it is proved by Plamondon, Pierre-Guy Plamondon. He will appear in the next week of this school, and he did it for skew-symmetric case, which I don't write it. Yeah, and this method uses the categorification of representation of a quiver, and this cannot be extended in a simple manner to a skew-symmetrizable case, and more general case was proven by very different method by Gross-Haken, Kontsevich, yeah. Published in this year, yeah, but paper appeared for about 4 years ago. And so they proved this together with another very difficult conjecture called positivity conjecture by the method of toric geometry, and they somehow construct the whole solution of this one, and showing manifestly that this cycles. But sorry, I have to write the statement. So the statement is each column of C matrix C of t at any point is non-zero vector And it has a definite sign. I'll explain what this means. It means C vector, each vector looks like, say, something like 0, 0, 2, 0, 1, something. Yeah? So there is no mixture of plus and minus. It might be, this one is plus and the other one might be minus. But so this statement, quite a simple one. So far, there is no elementary proof. I mean, this should be actually the consequence of just the mutation formula. One simple mutation formula. But every effort so far to explain this just from exchange relation is not successful. It's an open problem. But there is some very some other method which can prove this, and this is very important property. It reminds me root property, right? So everything is a positive vector, negative vector is a kind of a root decomposition of a positive part and negative part. And so there is somehow its connection to root system, but I don't mention this at this moment. Anyhow, once you have this result, then many things are a result. Yeah? So this is based on that very non-trivial result. So in particular, first we can define the following quantity, epsilon ti, which is a sign of ice column, so maybe ice column, yeah, of C vector, C of t, yeah. So I said this is not this is non-zero vector, yeah. So in this case, this one has a plus sign. Then we said it's plus, yeah. So those are plus or minus, or you identify it with the number 1, 1, and minus 1. Okay? And I use this quantity, and I call this tropical sign. So existence of this is very non-trivial based on this theorem. Yeah? But having these things, many things becomes very simple, and that's I'm going to explain. So next I'm going to explain the duality of these things, which is not clear at all in the original definition of mutation. But having this tropical sign, then duality becomes manifest. So what I said is duality is a consequence of sign coherence. Yeah? And that I'm going to explain. C and G matrices. Okay, so I'm going to erase this section. So first, I want to rewrite C-matrices formula, which I wrote here using a tropical sign. So once again, I write the following. So C matrices are uniquely determined by the following initial condition and mutation. Yeah. Now you understand when this formula applies, so I omit this T prime something, and this one I'm writing exactly the same formula. This is true for when J equals K, but maybe with different choice of indices. Yeah. this one formula is exactly what I wrote yesterday. Yeah. And I put some space here. It's maybe okay. Maybe I don't do this at this moment. T. So when you look at this formula, you don't see anything good at first sight. But now I first of all point out the following things. Here we have plus and minus sign. But actually you can replace this, instead of plus, you can change this to minus. And simultaneously, you change it to minus to plus. So you take plus minus or minus plus. And they give exactly the same formula. It's not that, so the formula, due to this definition, has two different expression for each choice of epsilon, plus or minus. Then if you have a minus epsilon here, then the total expression is the same. Yeah. We use this fact. So, and in particular, this formula as a transformation of a C variable, it is a piecewise linear transformation because of this one. But having this kind of degree of freedom, you can kill this part. I'm going to explain. Due to this tropical sign, then you end up with a linear expression. And that is a good one. So set epsilon to be, exactly this one. The purpose of this choice is then this factor will be killed. Okay, let me first do it step by step. So this one goes to C I K plus, and because I insert this, we have this one. On the other hand, this part, especially this part, becomes minus. I choose epsilon to be this one, so a minus epsilon k t c I k t. Now, you know, this one might be plus or minus, which I don't know, but the sign exactly coincide for any choice of I. That is sign coherence. So sign coherence means each k column, whatever I is, this has a definite sign, and I choose to kill it. So it's multiplying, it is a positive number. We have minus number here, so it's a minus sign, so it will be killed. So by this specialization, this one term disappears. So in conclusion, we have a much simpler system. So this is a formula. This is a formula. New formula for mutation. You can't do it without knowing this deep theorem of sign coherence. Yeah. And so this C-matrices is simplified a lot. And similar things happen for G-matrix. And after that, duality becomes manifest. So next, I recall you the mutation of G-matrix, which I wrote yesterday. But it's okay that you don't remember it at all. I just write it again. Now, G-matrix. These are determined by the initial condition such that G T0 is identity matrix and the mutation formula are something not simple at all. It looks, this one is simple, z of ij, t, if I, sorry, j is not k. Meanwhile, when the j is this number is k, and the formula is more complicated, I k plus z I t l is indices to be sum up, and b I k of t, and we have minus sign. It's not a misprint, and also we have missing t. It's not a misprint. It's an initial B matrix, and we have minus c l k plus when I is equal to k. Yeah, I wrote this formula yesterday, but let's look it a little bit closer this time. Yes, and once again, similar things happen. So this formula, we have minus here, but you can replace it to plus simultaneously. Then this whole expression is the same. You can prove it not just identity, but using mutation formula itself. So it's a little bit technical equality, but you can, point is you can replace it simultaneously to your choice of plus and minus. It gives you exactly the same quantity. Yeah. So, and using this freedom, degree of freedom, you may erase these things. Yeah. So it's a kind of a strange thing. So it is not closed by G itself, but it also contains G here. But again, a setting epsilon to be, I do the same thing. So the same, use this tropical sign here. Then this portion becomes minus, maybe minus sign. Let me see. Maybe minus, yeah. Ooh. I'm a little bit confused. So give me a second. Wait, confused. My note. Yes, probably it is correct. So, what is the best way to write it? So, just set as, so write this portion minus epsilon and choose epsilon. And then exactly by the same consideration. So, due to sign-coherence, this one is k, so they have the same sign, so the product is positive, and so we have minus sign, so it becomes 0. So this portion, whatever error is, disappears. So this is an important point coming from sign coherence. Yeah, for every law, it has the same sign, so it can be managed by single sign. On the other hand, this one is plug in these things. We have some things. And so once again, this becomes a linear system with respect to Z matrix. And you see some duality structure already. Yeah? And in fact, it is a kind of transposition if you make a transposition of matrix sense of this one, you basically have these things. And with some a little bit more technical calculation, but anyway, due to having this form, foreign duality is already manifest. 3. The duality between C and G vectors. This resulted due to myself and Andrei Zelevinsky. Under the assumption of sign-coherence, when we prove this, we claim that under the assumption of sign-coherence, this duality happens. But now it is proved, so it is really without any assumption. So the claim is this. So let D be a skew-symmetrizer of your exchange matrix. So yesterday I mentioned that if you multiply something, it becomes skew-symmetric, means a skew-symmetrizer. And by mutation, this skew-symmetrizer preserved. Namely, it is a common skew-symmetrizer for any exchange matrix. Then using this matrix, G matrix at point T, and C matrix at point T are related by the following simple formula. If you multiply the inverse, this is the diagonal matrix, we have inverse, and make a transposition, and maybe multiply this to this, gives you identity. Which means, especially when D is identity, so when B is skew-symmetric already, then this D does not, when D is I, the formula is much simpler, so D matrix and D matrix are, in fact, dual matrix each other. Yeah. So in particular, it means G matrix is completely determined by C matrix. It's just inverse, transpose of the inverse matrix. So our duality holds. Yeah. And in a general case, you have some correction by this skew-symmetrizer. Okay, so I have proved my second subject, and one more remark which is useful is the following statement. Exchange matrix itself is also so when you multiply this D matrix, and you can obtain this from the initial DB matrix. This is the initial one by following multiplication. You just multiply the right C matrix, and from the left C matrix at T, it's transpose. Yeah. Then we have such formula. And so this is a formula. And of course, to define this matrix, you need the information of B matrix. But after that, this BT matrix can be obtained just from C matrix. Yeah. So so far, what we have accomplished is if you have a C matrix, it determines uniquely G matrix and also B matrix. Yeah. So it's already important element of our seed and also a part of our C. So only missing is F polynomials. Yeah. And if you C matrix determines uniquely F polynomial, that is a result what we want to have, and that is the last section. And I want to use this property in view of the periodicity problem in cluster algebra. You talking about duality? Yes. Sorry, I can't hear you. That's true. I mean, well, but you can also prove this. I mean, also, so it's also, we can prove. It's not clear. Once, I tell you once again, if you have this kind of reduced formula, and then you can calculate these things. This gives you exactly a mutation formula of exchange matrix. Exchange matrix has two some additional terms, right? And they come from this part and this part. It's already included in the formula of exchange matrix. Yeah. 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 So this one is a consequence of sign coherence, actually. Without it, it's not clear at all. Yeah. There are many interpretations of this formula, so I want to explain, but I don't have time, yeah? So I'm going to do it personally. Yeah? So anyhow, thank you very much for asking, and it's good timing. And finally, let's talk about periodicity in cluster algebra, which is a very important subject, and the tropicalization. So maybe I start from motivating our problem of periodicity. So suppose you have some seed. Yeah? First, I just define the notation of action of permutation. Yeah? Of seed, for seed. So n is a rank of a seed, and we suppose we have a permutation. Yeah. Then we define B action of this with something new seed, which is determined that B prime ij is so everything is given by derivative of index of B and X and Y by simultaneous. It's a right action, but I don't mind. Anyway, so this is just a notation. And using these things I define, suppose you have a sequence of mutation. Means, so it's kind of a discrete dynamical system. So I introduce the discrete time 0 to 4 for the notation. It's a convenient y0. Suppose this is the initial one, and at time 0, you make a mutation at a given direction, k0. And so now you have a discrete time 1, and you have some seed, and k1, and so on. And you repeat, say, t times, yeah? For example, t minus one times. So starting from 0, and so t times the last one is this one, and you end up with something, yeah? I mean, just this is a notation for the sequence of mutation and suppose we say this is a sigma periodic if and only if if we have the last one coming back to the original one, modulo this simultaneous change of indexes, namely sigma b0, x0, and y0. Then we call this sigma periodic. So it's kind of partial periodicity, and if sigma is an identity, then it's really a complete periodicity. Now, such example already appeared in the lecture by Jacob, type 1 case, but it is called, in my, someone may call this pentagon relation. Pentagon relation. And this is a type A2 case, but it can be phrased in a more general way. Suppose you have your exchange matrix is, so this is rank n case, but suppose your just first section would be, say, something 1 man. So this is type X, and everything, other things is anything if it is a skew symmetrizable. Yeah. And we make a mutation starting from your seed at 0, say, starting from, and you make a mutation 1, 2, 1, 2, 1. You do it 5 times, yeah? Then it coming back to the original one, modulo, this sigma is, in this case, transpose of 1 and t. So this is, the fact is, this is always, whatever this matrix is, and whatever the choice of coefficients, this is a periodic. Very periodic, yeah. This is a transposition. Of 1 and 2. Yeah. And such is an example, and there are many such periodicity in cluster algebra. And studying them is very important, and it's is related to the dilogarithm identity, which I'm going to explain in the next lecture. And but anyway, so this one is one, and okay. And in general, it's very difficult to prove such a periodicity explicitly. In this case, you can do it by hand, and some other cases, you can do it by computer, but the computer usually does not help so much. Usually, even you use very good computer with a lot of memory, maybe repeating mutation maybe 5 or 6 times already. Computer stops answering, and maybe after three days later, it gives answer that it is out of memory. Something like that. So proving periodicity is one big issue, and I want to say that having a periodicity, you have a very nice consequence from this. That I'm going to explain later. Anyhow, this usually proof is very difficult. Yeah. But the result I'm going to explain drastically simplifies the problem. And in fact, you can prove such periodicity. That is the tropicalization result, dead tropicalization. I have already hinted this at the beginning of my section, but the following result recently due to okay, I first tried dead tropicalization. So this result, again, first, when skew-symmetric is, this is the consequence of the result due to Plamondon. by the method of categorification. And, but this, once again, is difficult to generalize to a skew-symmetrizable case. But recently, some nice paper appeared by Cao-Huang-Li and Li, and that says the following claim. Suppose we have let T is some T two points in regular N tree, and suppose that there your C matrix T and T prime are related by some permutation of 1 to n in the following way. So it is a counterpart of the sigma action of sigma for C matrix, because it is similar to this one. And from this, you can conclude that, so it means C matrix part of the seed attached to the cluster pattern has a sigma kind of relation. Then from this, you claim that your sigma T is maybe is written as related by this. Yeah. So whole seed are related by this property. And proof is actually this paper is only 5 pages long, and the proof part of this theorem only take 1 page. And I have already gave almost all necessary information in my lecture, so you can read it by yourself. And argument is very elementary and but very clever. And they use so proof uses proof of Cao-Huang-Li uses the following things. First of all, they use duality of C and G vector, what I explained. Also, they use separation formula, which I have already explained. And also, they use positivity of F polynomials, which is also one very non-trivial result. Positivity of F polynomial. And you're just using this, those are non-trivial results, but then after that, this is an easy consequence. And I really want you to read this paper to check that you understand my lecture well. So, conclusion, I have already get the nice result. So it means, once you have a periodicity for C matrix part, then from this, whole sigma periodicity of whole seed follows. Yeah, and that is the main. So corollary. I can claim this in the context of periodicity. So suppose you want to prove such a periodicity, and then you really have to calculate all these. Rational transformation or composition, it's in fact impossible. So, but you can reduce these things just looking at the associated C matrix things. So you just calculate to CT, and if this has a sigma periodicity, then that's it. Then you have sigma periodicity. That is a very powerful result. So because so I rephrase this result in the context of periodicity in the following way. So sigma periodicity of C matrices, which is a disguised form of tropical Y variable, by the way. I have already explained this, yeah? Imply the sigma periodicity of whole seed. So And in particular, if you especially are interested in some periodicity or your X variable periodicity or Y variable periodicity, still everything reduced to the problem of this C-matrix transformation, and it's I already erased. I'm very sorry about this, but it's just very simple system, linear system. Computer can easily calculate, first of all, and moreover, in many contexts, this C-matrix mutation formula, which I have written in that way, is realized as certain transformation of on-root system. So in that way, you can really prove the periodicity when it is necessary. And I close my lecture to give some history of the subject. So in 90s, so I often say that it is before cluster algebra, BC, yeah. So in 90s, there are a lot of conjectures, yeah, on a periodicity of what is called Y system, which appear in the context of conformal field theory and integrable system. Yeah? Starting by Aloysius Zamorozhkov, and many people, including myself, predict such things from the kind of consistency of the some physical model. And many people try to prove it, and they failed. By the same reason what I'm kind of, so this Y system is a algebra functional recursion relation. So to really solve this is impossible even by computer. But 00 is cluster algebra introduced, and then soon it is recognized that this Y system is exactly a part of Y pattern. It might be a coincidence that this Y and Y, but maybe Zelevinsky may somehow use the same variable, which I'm not quite sure. Now I don't know. But anyway, so this Y system is actually embedded in a cluster pattern, Y pattern, and so this periodicity problem is turned out to be the periodicity problem of cluster pattern just like this. And then after that, these things, technicality has developed, and say around 2010, and after that, many, so almost all, I mean, all maybe probably all known conjecture is proved by using this tropicalization method. And it's not just a tool, but without this, you can't do anything. So this is really the reason why periodicity is justified. So cluster algebra, cluster pattern structure is responsible for the periodicity of this Y system. Is what I learned after 20 years of studying this. Okay, thank you so much.
Any questions? So,
Theorem 5, yes. Yeah. Well, you can maybe. Well, so there is another argument which you can follow, but somehow my point is as follows. So in the future, it should be possible, and it should be given a new proof of sign coherence and positivity without using toric geometry. That is my wish. And what I said is this thing is just consequence of these two important theorems. So I somehow make the logic clear. How you can prove this. Once you have a more elementary proof of sign coherence and positivity. Yeah? So then this is a corollary of this. Yeah. So I agree, there will be another proof by this constructive method by Grosshack and Kiran concept. Sorry, I have some problem over hearing. With period, which one? Pentagon there? This is true. Yeah, for any choice of B matrix with such type, and for any choice of coefficients. In fact, it is a consequence of that, but anyway, it is true, yeah.
Any more questions?
Yes. Yeah. It's the same thing. So I just explained the intrinsic meaning of C vector in that way, but you have separation formula which is applicable to any P, and using this result, so for any choice of P and any choice of initial Y variable, still you just calculate C matrix, whatever it is. It independently exists. Yeah. It only defined through the B matrix. Yeah. So. I just explained the intrinsic meaning of the C matrix. Yeah. But C matrix you can define just plainly, just as matrix. Yeah.
Thank you very much.